So another quick mechanism video, learning how to get the stuff on the left to whatever's on the right here. And the only thing that we're allowed to use is borane. So give it a try real quick and we'll work on it after. So the takeaway here is that borane is actually a Lewis acid. So remembering from general chemistry, Lewis acid is uh, not a Bronsted acid. It's actually an acid that has empty p orbital that can accept electrons. So in this case, we're going to see uh, boron here take electrons from one of these oxygens. So first thing we should suggest is that this oxygen right here will act as the donating atom where it donates these electrons to the empty p orbital of that boron atom, and we will get this down right here. So because we just attached that attached borane to this oxygen, we now need to satisfy some charges. So you notice real quick, I gave that boron a negative charge because it gained electrons, and the oxygen a positive charge because it gave up some electrons. Best way to satisfy this is to push electrons up so that the oxygen becomes neutral again. So when the oxygen becomes neutral again, this is what we'll get. So at this point, we just need to satisfy charges again. You might think you're putting a positive charge on an alpha position to a carbonyl, which is already feeling a relatively large delta positive due to the inductive effect of that carbonyl. However, this next step happens uh, just right after the previous one. So you'd almost probably get away with saying, if we went back to the previous intermediate, you'd almost get away doing it all in one step. I did it in two, but again, you might be able to get away with doing it in one. But this happens so quickly that it doesn't really even feel that positive charge that long at all. We do this to satisfy that positive charge. Satisfying the positive charge gets us to this next intermediate. So this is our final intermediate. Our next product is going to be our final product. So that's nice. At this point, I've actually also forgotten to put in a positive charge, but there should exist a positive charge right here. So let's just track atoms to make sure we know what's going on. This carbon that is connected to the oxygen is going to be this carbon. Okay, so in red now, the carbon that helped form the six-member ring is this carbon. So we just added that carbon. That existed right there. So the carbonyl that existed in the previous intermediate right here, and that kind of turquoise color, was one carbon away from the red. So we have it one carbon away from the red right there, so that's good. And now in this kind of baby blue color, the carbocation, excuse me, the carbocation rearrangement that occurred was facilitated through this carbon, and we see that carbon is right here. So it ended up being one away from the red, and you can tell from the mechanism it will be a cross from, or you can think of it as two carbons away from the purple. So we have all of our carbons right, so that's great. That means our positive charge is also correct. So at this point, we are just going to reform, or I guess we never really had, but we are going to form a carbonyl to get rid of that positive charge. So we can say that these electrons that were originally bonded to borane come down, forming a carbonyl, satisfying the positive charge and letting borane go back to a neutral state. So that's the full mechanism. It's only a, what is that, four-stepper. It's not that difficult, just recognizing that in this problem, borane is a Lewis acid.